at a time t2, because here Bob only concerned about the measurement outputs B and Y classically, and he does not care about the post-measurement states. So all he has to do is to use the projective measurement to describe his measurement process. Okay, so if you want to compute the probabilities of Alice measurement outcomes, you just take a trace of the post-measurement states. And if you want to compute the Bob's measurement outcomes, these probabilities, all you have to do is to take a trace of the Bob's measurement times the states. So combining these two thin scatterers, you can obtain the quantum relations of these probabilities, so which is with these forms. So the trace of Bob's measurements times post-measurements of Alice. Okay, so now the equations of characterizing quantum temporal correlations is equivalent with the following statements. So given some probabilities PAB of XY, there states rho, instruments I, and projectors E, such that these probabilities can be written in this form. So this is the question we want to ask. Right? So the problem is generally hard to solve because you have to find out all possibilities of these measurements and all possibilities of these instruments. So an alternative way is to develop some necessary conditions. So this means that if this probability has a valid quantum descriptions, then this necessary condition holds. So we want to find out these conditions. And this technique is also called semi-definite realizations, so which was already proposed by Dorothy Liang, Turner Weiner, and Navas Guest and Pironion as seen in 2008. Okay, so let me show again our goal. So if this probability has a valid quantum description, we want to find out some necessary conditions holds. So here we consider a complete positive map E acting on the post-measurement states. And we denote this gamma X as the after the map on this post-measurement states. Okay, so this figure reminds us that what is the Ix over here? So Ix of rho is the post-measurement states after Alice measurements. And the E over here has nothing to do with the, what happens in the real lab. It is just some mathematical formulations. And the E, because it is a complete positive map, so it can be written as some cross-operation form. And the K, we can define it as this way. So it maps from the space of N to the space of I. And S over here is some Bob's measurements and their products. Okay, so after all of these things, we can eventually write down the final form of this gamma. So it is actually, it's just a matrix whose i's row and j's columns is these terms. So the trace of the I of row times Sj dagger times Si. Okay, so we call this gamma X, the set of which is the instrument moment matrices. And the elements of these instrument moment matrices, there can be categorized as three kinds of values. So the first one is the probabilities PAB given XY. So this happens when Sj dagger times Si, they are equal to the projectors EBY. And the second type is zeros, and this happens when Sj dagger times Si is equal to the products of the projectors with the same measurement inputs Y, but the different measurement outcomes B and B prime. So the last possibility is that when Sj dagger times Si is equal to the product of projectors with different measurement inputs Y and Y prime. And this term actually is not as accessible in the real experiments because we don't know what is the underlying state is. We also don't know what is the measurements performed by Bob. So the only information we know in this kind of experiments is the probabilities. So therefore, we call all of these terms as some unknown variables. Okay, so now we are going to introduce these necessary conditions. So actually, this instrument matrix has some important properties. So one of the most important is that it has to be positive semi-definite if the density matrix used for describing the states is positive semi-definite. Okay, so but not the vice versa. So from here we can see that the positivity of this instrument moment matrices actually serve as a natural constraints for characterizing quantum temporal correlations. Okay, so here we are going to give examples of how to use these conditions to compute some bounds of the temporal CHU inequalities. So the goal is to maximize these terms, and under the constraint that this necessary condition holds. And maximization is taken over all the unknown variables in the previous pages. Okay, so actually this is a semi-definite program, and this can be solved efficiently by personal computers. So our numerical results show that this gives us the value of force, and this can be achieved by qubits plus non-projective measurements. So actually this bound is tight. Okay, so as we mentioned earlier, we don't make assumptions on the underlying states nor the measurements. So actually we are in a device-independent scenario. But we want to ask more. So can we apply additional constraints to obtain different bounds? So the answer is yes. So for the second constraints we are actually considering is the dimensional constraints. So here we impose the dimensional constraints on the underlying states and the measurement involved. So we ask the dimension, upper bound of this dimension is D. So if this is the case, then this implies that not only the instrument moment matrices has to be positive semi-definite, but also this gamma has to be belong the set of GD. So the GD here means that here. So recall that the instrument moment matrices is defined in this way. So if when we say this gamma belongs to the set GD, we mean that the dimension of the post-measurement state has to be D, and also the dimension of the Bob's measurement has to be equal to D. All right, so here we again test the dimension when D is equal to 2. So we again obtain the upper bound with the value of 4. And this happens because we recall that this value of force can be achieved by qubit plus non-projective measurements. So here we only impose the constraints of a dimension, but we don't ask any constraint about projective measurements or non-projective measurements. So for qubit measurements, we have to, if we want to impose these constraints, we have to link this connection, link the idea to the idea of the rank. So for projective measurements, the rank is equal to 1. And for non-projective qubit measurements, the rank is equal to 2. So we would like to introduce the rank constraints to enforce the measurements to be projective measurements or non-projective measurements. All right, so the third type constraints is to introduce the rank constraints on Bob's measurements has to be upper bounded by the value of K. And if this is the case, then this implies that gamma has to be of the set inside the set of GDK. So when we say gamma is in a member of GDK, we mean that the dimension, not only the dimension of the systems has to be equal to D, but also the rank of Bob states has to be equal to K. Okay, so after applying these constraints, we again set that the D equal to 2 and K equal to 1. So this means that we apply the projective measurement constraints. And we obtain the value of 2 square root of 2. So from here we can see that we actually obtain different bounds. Okay, so lastly, we consider the no-circling in time constraints. So this constraint tells